Hello everyone. Welcome to another episode of Deep Dive Knowledge Talk. I am delighted to have this opportunity to delve into the exciting and innovative world of knowledge graphs, KGS, and their significant role in enhancing Retrieval Augmented Generation, RAG systems. Let us dive right in. In the realm of artificial intelligence, the fusion of KGS and RAG systems has garnered considerable attention lately. Could you provide some insights into how KGS contribute to improving the performance and accuracy of RAG systems?
Sure. Knowledge graphs, KGS, are like huge interconnected webs of information. They organize data into different entities and show how they are related to each other. Retrieval Augmented Generation, RAG, systems use these KGS to understand the context of a question and generate more accurate and relevant responses. Imagine you have a question about the history of the United States. A RAG system would search through a KG to find information about the country, its presidents, important events, and so on. This helps the system to generate a response that is not only factually correct but also tailored to the specific question. By using KGS, RAG systems can also learn from new data and improve their responses over time. This is especially useful in fields where knowledge is constantly changing, such as science and technology. Here's a simple analogy to help you understand. Imagine a library with lots of books on different topics. A RAG system is like a librarian who can quickly find the right books for you based on your question. KGS are like a map of the library, showing the librarian where to find the books they need. By using the map, the librarian can find the books faster and give you more accurate answers. In the same way, KGS help RAG systems to find the right information and generate better responses.
Thank you for that clear and informative explanation. It is evident that KGS play a vital role in enhancing the accuracy and relevance of RAG systems. To further explore the practical applications of this integration, could you provide some real-world examples of how KG-augmented RAG systems are being utilized in various domains, such as healthcare, legal services, and education? Additionally, what are some of the key challenges and limitations associated with the integration of KGS and RAG systems? How are researchers addressing these challenges?
Let's say you are searching for information on the internet using a search engine. The search engine displays a list of relevant websites that contain information related to your search query. However, if you want to find more specific information or get a comprehensive overview of a topic, you can use a knowledge graph. A knowledge graph is a database that stores information in the form of interconnected nodes and edges. Each node represents an entity, such as a person, place, or thing, and each edge represents a relationship between two nodes. Knowledge graphs are used by search engines and other applications to provide users with more relevant and comprehensive information. RAG, Retrieval Augmented Generation, systems are a type of natural language processing, NLP, model that uses knowledge graphs to improve the quality of their output. RAG systems work by first retrieving relevant information from a knowledge graph and then using this information to generate text. This approach allows RAG systems to generate text that is more accurate, informative, and coherent than text generated by traditional NLP models. Here's a real-world example of how knowledge graphs are used in RAG systems. Let's say you are using a RAG system to generate a news study about the latest developments in the tech industry. The RAG system would first retrieve relevant information from a knowledge graph about the tech industry, such as information about the latest products, companies, and trends. The RAG system would then use this information to generate a news study that is accurate, informative, and relevant to the latest developments in the tech industry.
Thank you for providing that real-world example of how knowledge graphs are used in RAG systems. It is clear that this integration has the potential to significantly improve the quality of text generated by NLP models. However, as with any new technology, there are likely to be some challenges and limitations associated with the integration of KGS and RAG systems. Could you elaborate on these challenges and discuss how researchers are addressing them? Additionally, what are some of the future research directions in this field?
Knowledge graphs and retrieval augmented generation, RAG, systems integration does have its set of challenges and limitations. However, Researchers are actively working on addressing these issues to enhance the overall performance and effectiveness of RAG systems. One of the key challenges lies in ensuring the quality and completeness of the knowledge graph itself. Inaccurate or incomplete information within the knowledge graph can lead to errors or biases in the retrieved information and subsequently affect the quality of the generated text. Researchers are exploring techniques such as data cleaning, knowledge graph refinement, and incorporating external knowledge sources to address this challenge. Additionally, the alignment and integration of knowledge graphs with RAG systems can be complex, requiring careful consideration of data formats, ontologies, and query languages. Researchers are developing methods for seamless integration and interoperability between knowledge graphs and RAG systems to facilitate efficient information retrieval and generation. Furthermore, the interpretability and explainability of RAG systems can be limited, making it challenging to understand the reasoning behind the retrieved information and generated text. Researchers are investigating techniques for providing explanations and justifications for the retrieval and generation process, enhancing the transparency and trustworthiness of RAG systems.
Thank you for providing those insights into the challenges and limitations of integrating knowledge graphs and RAG systems. It is evident that researchers are actively addressing these issues to improve the performance and reliability of RAG systems. As you mentioned, one of the key challenges is ensuring the quality and completeness of the knowledge graph. Since knowledge graphs are often constructed from various data sources, they can be prone to errors, inconsistencies, and biases. How are researchers approaching the task of evaluating and improving the quality of knowledge graphs? Additionally, are there any specific techniques or methodologies that have shown promise in this area?
Researchers are taking various approaches to evaluate and improve the quality and completeness of knowledge graphs. One common approach is to use metrics such as precision, recall, and F1 score to measure the accuracy of the knowledge graph. Researchers are also developing new techniques to automatically identify and correct errors in knowledge graphs. Additionally, researchers are exploring the use of machine learning and natural language processing to improve the completeness of knowledge graphs. One promising technique is to use natural language processing to extract information from text documents and add it to the knowledge graph.
Thank you for providing those insights into the evaluation and improvement of knowledge graph quality. The use of metrics like precision, recall, and F1 score, along with techniques for automatic error identification and correction, is crucial for ensuring the accuracy and reliability of knowledge graphs. Another important aspect of knowledge graph quality is its coverage, which refers to the extent to which it contains information about the domain of interest. How are researchers addressing the challenge of improving knowledge graph coverage, particularly in domains where information is scarce or rapidly changing?
Researchers are actively exploring several approaches to improve the coverage of knowledge graphs, especially in domains where information is scarce or rapidly evolving. One common strategy is to leverage external data sources and integrate them into the knowledge graph. This can involve extracting information from unstructured text, such as news studies, scientific publications, or social media data. Another approach is to employ machine learning techniques to generate new knowledge or infer missing information based on existing data. Additionally, researchers are investigating ways to utilize user feedback and contributions to expand and refine knowledge graphs, ensuring they remain up-to-date and comprehensive.
Thank you for elaborating on the approaches for enhancing knowledge graph coverage. Utilizing external data sources and employing machine learning techniques are valuable strategies for expanding the scope and richness of knowledge graphs. In addition to these approaches, are there specific methodologies or best practices that have been found to be particularly effective in improving knowledge graph coverage, especially in domains with limited or rapidly changing information?
There are several effective methodologies and best practices that have been proven to improve the coverage of knowledge graphs, especially in domains where information is limited or rapidly evolving. 1. Automated knowledge extraction. Utilizing advanced natural language processing, NLP, techniques and machine learning algorithms, knowledge graphs can be automatically populated and updated by extracting information from unstructured text data, such as news studies, and social media posts. This automation helps in expanding the coverage of knowledge graphs, particularly in domains where information is continuously generated and updated. Crowdsourcing and community curation. Engaging a community of experts, researchers, and enthusiasts to contribute their knowledge and expertise can significantly enhance the coverage and accuracy of knowledge graphs. Crowdsourcing studies and community-driven initiatives allow individuals to add, verify, and refine information within the knowledge graph, ensuring its completeness and reliability. 3. Leveraging ontologies and taxonomies. Incorporating existing ontologies and taxonomies into knowledge graphs provides a structured and organized framework for representing and interlinking concepts and entities. This helps in expanding the coverage of knowledge graphs by establishing semantic relationships between different domains and subdomains, enabling more comprehensive and accurate query answering. 4. Continuous learning and incremental updates. Implementing continuous learning mechanisms allows knowledge graphs to adapt to evolving information and emerging trends. Machine learning algorithms can be employed to monitor changes in data sources, identify new entities and relationships, and incrementally update the knowledge graph, ensuring its currency and relevance. 5. Collaboration and data integration. Establishing collaborations with other organizations and leveraging shared data resources can significantly enhance the coverage of knowledge graphs. By integrating data from multiple sources and perspectives, knowledge graphs can gain a more comprehensive understanding of different domains and provide more holistic and reliable information.
Thank you all for joining us today. I would like to take a moment to recap the main points of our discussion. We learned that knowledge graphs, KGS, play a crucial role in enhancing Retrieval Augmented Generation, RAG systems, by providing a structured and interconnected organization of data. This results in improved accuracy and relevance in various real-world applications such as healthcare, legal services, and education. However, challenges exist, including ensuring KOD quality, aligning KGS with RAGs, and ensuring interpretability. Researchers are addressing these challenges through data cleaning, refinement, and external knowledge integration. Evaluation and improvement of KG quality are achieved through techniques like precision, recall, and natural language processing. Meanwhile, methodologies such as automated extraction, crowdsourcing, ontologies, and continuous learning enhance KLU coverage. By leveraging KGS, RAG systems can effectively retrieve and generate more accurate and relevant responses. This has significant implications for various domains and opens up exciting possibilities for future research and development. Thank you again to our guest researcher for sharing their insights with us today. I encourage you all to continue exploring the exciting field of KGS and RAGs.